I think we'll go ahead and get started with the main part of the conference, having done the tutorial lectures yesterday. So I'm Rob Neal. I'll say a few words in a minute, but first we'll start with a word greeting from the department chair here, Garth Isaac.
Welcome, everybody. I've been on the other side of this and know how much you hate listening to someone who's not in the area, so I will talk very quickly, but this is my chance to thank some people in the department. So Rob and C and Daniel are the local organizers, and wonderful to have as colleagues and wonderful that they brought this conference here. You will have met Mandy and perhaps Marianne, who are department staff. Thank them. They are there to help. They'll do their best. And Cheng Hung, our graduate student, who's also helping out. I just want to welcome you all here. Take advantage tomorrow when the weather is nice. If you have a chance, if you like a view, go up to the top of the mountain, our other campus. Go over and see our newly renovated math building. It's wonderful. We've moved in 4 months before COVID, so we're finally settling in. And have a great conference. Glad to see everyone here. It's exciting to see a conference in person after 2 years.
Dr. John, the chair of the long-term science committee for SSP.
Thank you very much, Professor Neal. And so just a word of welcome for everybody. It's just such a pleasure to have a conference in person. And, you know, there's also folks who are on the phone. I see there's even people who are in Japan right now connecting for this morning's session. So let's all stay engaged with the folks in the room, with the people on the line, because this actually may be the new normal. We're not really sure how long this sort of setup will last. Thank you all very much for coming to this conference. And you know, this is a conference series which has, as far as I understand, has been running since 1981. And I think that last year was the only year in the entire history of the conference where we had to cancel because of COVID. It's a 100-year event, of course, so on a 30-year span, you're going to have a 100-year event. It takes precedence over a 30-year or 40-year span, whatever it is. So again, we're just so pleased. We were supposed to be here last year. We're here this year in person. Thank you again. And again, I want to iterate again with the chair of the department said, you know, the organizing committee here, the scientific organizing committee here, has done such an extraordinary job. Thank you very much.
Perfect. So thank you. Thank you, Garth. If I were to add a few personal notes, I will say SSP 2020 at MSU was the very last conference I attended in person that had an in-person component that I was involved in even. I see some nods. I know some faces from there. COVID was starting to come onto the scene at that conference. And there was a conference actually a week after that I was supposed to go to that was canceled. And so we really slid it under the wire. Then everything shut down. We had to cancel last year. So the fact that now, almost 2 years, essentially to the week after the last in-person conference I was at, we have another in-person conference, also SSP. I'm very happy for. I'm very grateful for everyone who made it here in person. I'm very grateful for everyone who made it here on Zoom. I understand after 2 years, a lot of people are Zoomed out, so I didn't even know how much appetite there would be to participate if you couldn't come in person. But we have quite a list of remote participants lined up for this conference as well, so I'm happy about that. I will also reiterate from a personal perspective, to the extent you find the conference to have been organized, that is due to the local organizers, C. Tang and Daniel Konis, my colleagues, also to Mandy Alford and Marianne Kent, who Garth mentioned, but who I will gladly mention again and probably one more time, if not more, before the conference is over, who have done a ton of work behind the scenes. I think you've met one or both of them when you checked in already. Well, I should thank Garth Isaac as well, who's been very supportive of the conference. I should mention beyond the usual suspects, Frederic is chair of the long-term scientific committee. I think in an ordinary year, that would mean he did very little, perhaps, leading up to the conference. In this unusual year, I shamelessly took advantage of his experience and generosity with his time to help manage some last-minute details of this dual format conference. So he deserves even more thanks, I think, this year than in a normal year for any success SSP is experiencing. Moving beyond people, organizations, we certainly should thank the NSF who generously funded us with a grant. So if you're being supported in any way, the NSF is a thank for that. Pavel Tuschenko, the program officer, would have liked to have been here. He's sort of local, he's at Drexel, but he's currently in Europe, I believe, for personal reasons, so can't make it here in person. We should also thank the Simons Foundation. You might know the NSF does not pay for coffee breaks, but it turns out that due to my colleague Joe Yukich and Garth Isaac, there was some Simons money spun off of Joe's grant that Garth allowed us also to use for the coffee break. So if you enjoy any coffee, that's not due to the NSF, that's the Simons Foundation. So you can thank the right pot of money for everything. Beyond that, the Institute for Mathematical Statistics, IMS, they are a co-sponsor of this conference. They've done a lot also to support us, to advertise us, to supply us with medallion lecturers, which is what you're actually here for. So in a minute, we'll turn that over to a proper math event. We have 2 IMS Medallion Lecturers. We're fortunate in that regard during SSP this year. And then the family of...
Can I add that this is the first time that there are IMS Medallion Lectures at SSP. So this is also a big deal.
That's a good, yes. So we're doing that for the first time, yes, which is great. We're thankful for that. Also, the family of Kailei Chung supports the aptly named Kailei Chung Lecture, which will happen this afternoon, Jennifer Cheas. So they've also been very helpful in supporting the conference. There are probably people I've forgotten. I think that's traditional. But that having been said, I will now turn it over to my colleague Daniel Konis to introduce our first speaker. We'll come to the proper math portion now.
All right, so Rob said everything, thanked all the appropriate people. I want to take the chance to say good morning to everyone and welcome to this first plenary talk of this conference. So it's a pleasure this morning for me to introduce Ramon van Handel from Princeton University. So Ramon received his PhD from Caltech in 2007. He joined Princeton first as a postdoc in 2008, where he went up the ranks, currently an associate professor there. He is a probabilist, an applied probabilist, active in looking at probabilistic principles in both pure and applied mathematics problems. In particular, he enjoys applications and connections to other areas of mathematics, in particular analysis and geometry. Among his awards and recognitions, Ramon has received an NSF Career Award, a Presidential Early Career Award for Scientists and Engineers, the Erland Prize, and multiple other awards. So each year, as was mentioned by Frederick, this is the first time at SSP, but each year the IMS, the Institute of Mathematical Statistics, nominates 8 medallion lecturers in fields across its range of areas of research. And so the award of a medallion from the IMS signals the honor inherent in being selected to give one of these lectures. So today, I would like to welcome Ramon to come up here. Today, the IMS awards the IMS Medallion to Ramon van Handel, who, for the lecture that he's about to give us, entitled Non-asymptotic Random Matrix Theory. Thank you very much for being with us.
This is what the medallion looks like.
It is a medallion. And I'm actually a 2023 medallion lecturer. So now that COVID has made all sorts of delays and cancellations, it's nice to have something from the future come out. Thank you, Daniel, and thank you very much to the organizers for organizing this conference and for inviting me. And it's a real honor to be here to give this lecture. So I'm going to talk about non-asymptotic random matrix theory. Let me say up front that this is joint work of several authors with Alfonso Bandera, with whom I've been working on this topic for many years, and Mike DiMargio, and my PhD student, Tatiana Barros. All of whose last name starts with a B, but that was an accident. I don't know what's the problem. Can everybody hear me? Can everybody see the board? Everybody's good? All right. So I have to explain to you what is non-asymptotic random matrix theory, but in fact, this term is used in different ways in the literature. And I have a very particular thing in mind when I say this, and I'm going to start by explaining what that is and what kind of questions we ask there. But before I do that, I should probably explain to you what is classical random matrix theory, right? Not this this different direction. So the theory of random matrices is very old, right? And the basic question in random matrix theory is, if I have a random matrix, right? It's a matrix with random discrete. And can we understand its eigenvalue? Right? That's the basic. Can we understand the behavior of its spectrum? It's a very basic question. But you know, what does it mean, a random matrix? Right? You have to have some sort of model of the randomness. So classical random matrix theory, if you want to caricature it, it is concerned with certain models of random matrices that are extremely simple. But about which you can say very, very precise things. In particular, most of it is asymptotic theory. So let's say exact asymptotics. I'll explain in a moment what this means, but you know, what is the most classical model of random matrix theory, right? Say that I take X to be a D by D matrix. Let's say self-adjoint. Self-adjoint is just, you know, for simplicity, so it has real eigenvalues, right? And with, let's say, IID entries above the diagonal, it means 0 and variance 1 over D. So this 1 over D is just a normalization that will make this matrix behave in the same way as I increase the dimension. So such matrices are called Wigner matrices. And they've been studied, you know, for actually since before Wigner, for probably more than 100 years. And the basic results in these, right, if you take such a matrix and you draw, let's say, a histogram of its spectrum, you see a beautiful shape arising. So if you histogram the eigenvalues of this matrix, you will see this beautiful semicircle distribution. And I chose the normalization here so that it shows between -2 and 2. So of course, for a finite matrix, there are D eigenvalues, so there you have some sort of histogram, right? But as you take a sequence of such matrices in increasing dimension, right, as the dimension goes to infinity, the histogram will more accurately describe this semicircle. And other things that you might expect about the behavior of this matrix are already actually predicted by the semicircle. For example, the largest eigenvalue of this matrix will converge to 2 as the dimension goes to infinity, right? That's not obvious, right? Because the largest eigenvalue of the matrix has mass 1 over D, right? It's 1D. So saying that the histogram converges to this doesn't say anything about a fraction of eigenvalues going to 0, but in fact, it turns out that the edges of the spectrum converge to the edges of the semicircle. And all of these things are exact in the matrix, right? So this is the exact asymptotics. That's like the large numbers for these random matrices. And in fact, for these random matrices, much bigger. This is only the very tip of the iceberg. What you can do is you can zoom in on the spectrum, so you see the spacing between the eigenvalues of order 1, and get exactly the description of the point process of eigenvalues in the limit. Is it a deterministic point process or something more complicated? It's real. And you know, and there's huge connections between these in classical analysis and dual probability. Okay, so you know, about such models, a lot of things are known. So there's beautiful asymptotic theory, right? That you have a sequence of very simple models with IID entries. It makes sense to take a sequence of such models as the dimension goes to infinity. And then you can study the asymptotics as the dimension goes to infinity, and you get all sorts of beautiful exact forms. So in a sense, I'm interested in the opposite extreme, which are matrices with random matrices with totally general structure. So, I mean, what does this mean, totally general structure? Well, let me already give one example that is, on the one hand, relatively simple, but on the other hand, it's completely outside the scope of this type of theory, right? So we are going to take this as the running example in these lectures. Running. Suppose that X is a D by D self-adjoint. Again, I take it to be self-adjoint just for simplicity, so that there's no eigenvalues, right? And let's take it to have 1D Gaussian. That's it. That's the assumption I'm making. The entries of this matrix are jointly Gaussian. So it's still a special case in the sense that I made some Gaussian assumption, right? But in other ways, this is a completely general matrix, right? For example, every entry can have a different variance, right? An arbitrary variance. And you can have an arbitrary covariance between the entries, right? So you can have all sorts of strange correlation structures between the entries, right? So I really made very little of modeling assumption here, right? So there's two things that you should, notice about this, right? This is already extremely general. So the arbitrary pattern of variances of the entries, the tendencies, etc. I'm really assuming very little about the structure of this matrix. I can take any pattern that I want, right? That there's another issue with such matrices, which is that, you see, if I take something like IID entries, right? Then there's a canonical way of taking a sequence of these matrices and increasing dimension and studying asymptotics, right? Because I can take entries with the same distribution and just make the dimension of the matrix larger and larger, right? But if I tell you, for example, that I have a D by D matrix, I'm allowed to pick arbitrary variances for the entries, right? There is no natural asymptotics, right? What does it mean to take the dimension larger and larger and larger and have the same model, right? I just gave you a D by D table of numbers, which are the variances of the entries and the covariances, etc., right? So the question here, right, there is no natural asymptotics. As D goes to infinity, right? So for what can we give as an example, right? Take your favorite, computer art, right? It's a 320, oh, okay, I'm already running behind on the times. 4,000 something by 2,000 pixel image, right? Each pixel has a grayscale, and I just take a matrix and I pick a bunch of random, right? I pick a bunch of independent Gaussians with these grayscale values as being their variances, right? Well, this is a fixed D by D, right, array of numbers, right? There's no natural way of letting D go to infinity, right? It is what it is, right? So even the type of questions that you might ask here do not necessarily make sense on this side, because the model itself is inherently non-asymptotic, right? So it's not just that we don't understand, right? On the one hand, this model is so general that it's not clear. What could you possibly say if you make no modeling assumptions, right? It's like I'm asking you to describe every random. And even if you were to be able to do that, it's not even clear how to formulate the same questions as you would over there, because there's no natural parameter to let go to. So what I mean by non-asymptotic random matrix theory is exactly this situation that I give you a given D by D matrix with some sort of arbitrary structure, and I'm trying to understand the eigenvalues of that matrix, right? And so we have to think about what kind of questions. Okay, so what is known about such situations? So it turns out that some things are known, but they're very crude. The natural way of studying non-asymptotic objects is to prove inequality. So to show some inequalities for how these eigenvalues behave for a fixed matrix. And there is basically one set of results that is known in the literature at this level of generality. And in the Gaussian case, the most basic result in this area is the so-called non-communication inequality. So suppose that X is a D by D random matrix with jointly Gaussian entries. And let's suppose for simplicity that we do zero. So, I mean, over there, I'm allowing an arbitrary, but let's suppose, for example, that we think mean zero. So the only thing that varies are the variances and the covariances. This is not so important, but just to make the results simple. So what this result allows you to do is it allows you to roughly pin down the range of the spectrum, right? So for example, here, the range of the spectrum was constant when I normalize by 1 over d, right? It's between -2 and 2. So here, what we can pin down is roughly the range of the spectrum. So if we take the expectation of the operator norm of x, so this is just the maximum of the absolute value. This norm is the maximum of the absolute values of the eigenvalues, right? So that's pinning down the range. So it's lower bound than the up to universal constant by the quantity, which is the expectation of x squared with the norm outside. So you notice that here the expectation is outside the norm, right? This is the expectation of the maximal eigenvalue, absolute value. But here the expectation is inside the norm, right? This is the largest eigenvalue of the deterministic matrix, the expectation of x, right? So this inequality is basically Jensen up to some concentration, right? So the point of this is that this object over here is only depends, or is completely computable from the covariance, right? The expectation of x squared, this matrix depends only on the covariance of the entries, right? So this is some explicitly computable quantity. Yes.
My apologies for interrupting. Isn't this the opposite of Jensen?
No, I'm bringing the expectation inside. The norm is convex. I'm bringing the expectation inside. If I had a square here, if I look at the L2, this is exactly Jensen.
Oh, yeah, okay.
Right? So by some concentration measure, right, the L2 norm, the L1 norm of these norms is of the same order. So this is not the non-unification inequality. This is the trivial side. Did I answer the question?
One more question.
Yes.
The x squared,
Yes.
does that mean multiply the matrix by itself?
Yep.
And then take the expected value entry-wise by entry-wise?
Exactly. Exactly. Right. So you see, this only depends on the covariance of the entries, right? Because if I take x squared, that's the sum over j of xij, xjk, right? So if I take the expectation, it only depends on the covariance of the entries, right? So this is an explicitly computable quantity in terms of the model description. Whereas this is some complicated quantity because the eigenvalues of the matrix are very nonlinear functions. Okay. But the real magic of this is trivial, more or less, right? The real magic is that you can reverse this inequality. That's not the efficient inequality, but up to some fudge factor, which is square root of the log of the dimension. If you think about it for a moment, then this is both a sort of amazingly strong result and a embarrassingly bad result, okay? It's an amazingly strong result because we made absolutely no assumption about the structure of this matrix other than that it was jointly Gaussian, maybe means 0, right? We have here a fixed d by d matrix. We made no assumption whatsoever. And nonetheless, we can pin down the range of the spectrum up to only a factor that's only logarithmic in the dimension, right? So, I mean, that's quite a precise result for making no assumptions whatsoever, right? But on the other hand, right, I mean, compared to what you can do in classical random matrix theory, this is completely embarrassing, right? I mean, the upper and the lower bounds diverge as dimensional. Is there another question? Yeah.
So, I mean, I don't know if this is at all relevant, but the square root of log of d, I'm guessing this comes from the Gaussian property.
Let's look at the example.
Okay,
So,
all right.
but these results, this is the basic result in a set of results known as matrix concentration inequalities. And if anybody here has ever worked in applied mathematics, I mean, they're very, very popular there. People use these things, you know, because if you're not a random matrix theorist, but you're somebody who encounters random matrices in the analysis of statistical problems, algorithms, these kind of things, your matrices rarely look like the beautiful models that you see metrics, right? And you need to deal with some complicated structured random matrices, right? And these tools are basically the only tools you have at your disposal. But these tools are very easy to use. They work with basically any structure, and you can pin down what you want to know up to square root log d, which is already quite good. So just to show you that you cannot hope to do better than this, at least in complete generality, let's look at two examples. So on the one hand, if we take an example of a linear matrix, right? So this is a matrix with let's say IID Gaussian entries. So when I write these G's, I mean these are normal 0, 1. right? And they're independent, and I normalize by 1 over square root b to make the variance 1 over a, right? So remember, what we know is that the expected norm of x is actually 2 times 1 plus below 1. We know this from classical random matrix theory, right? Because this is a situation where the spectrum looks like that, right? So classical random matrix theory tells us that. And in this example, you can very easily compute that the expectation of x squared is the density matrix, right? So this object is 2 plus below 1. This is 1, right? But this is square root log d. So this is very embarrassing, right? In the most basic model of random matrix theory, the non-unification inequality is off by a factor square root. It's a very bad inequality for classical random. On the other hand, here is an example that looks nothing like a classical. I just take a diagonal matrix with IID standard Gaussians on the diagonal and zeros everywhere else, right? Then the expected norm of x, what is the largest eigenvalue? Well, it's just the largest diagonal entry, right? And the maximum of d IID standard Gaussians is of order square root log d, which is 2 log d. And here, obviously, the expectation of x squared is also good. And here you see that the upper bound here is sharp. So you cannot read this square root log d over here. The upper bound is sharp, and the lower bound is off by a lot of time. But both of these have exactly the same expectation of x squared. So you cannot tell the difference from this quantity to the upper bound. So this shows that, you know, these inequalities are somehow, in some sense, they're the best you can hope for, right? You cannot hope to improve them because given the same data about covariance, right, both the upper bound and lower bound. And so this was really it, in some sense, for these kind of models for a very long time. But one has, you know, for specific models, like for Wigner matrices, where you have exact asymptotics, you can compute things very precisely. But under completely general assumptions, all you have is these kind of crude tools, which are great because they allow you to say something about these matrices under no assumptions. On the other hand, they provide very weak information. They do not even give you the range of the spectrum up to a constant, right? Let alone providing exact information. So a problem that I've been interested in for many years, and my co-authors and other people who think about such things, is very modest. We had a very modest goal, which is to try to do better than this. To try to explain, at least for which, I mean, forget about getting the sharpest audits or something like this. Just try to explain for which matrices this square root log is. Because it turns out that if you look at explicit examples, for those examples we compute, and of course there are many explicit examples we compute, it turns out that this situation where this square root log d is there are very rare. Okay, so they're here for this diagonal matrix, and that's more or less the only case, or things that look like this. Right? And as soon as one departs a little bit from this kind of matrix, it turns out that this square root log d is almost never there. Which means there must be some explanation. So, you know, it's sort of a long-standing problem to try to find better bounds of this kind. Who cares about the constants? Forget about the constants. We have we're not very ambitious, okay? Because our assumptions are so general. What can we hope to say of an exact nature? Let's not be too ambitious. Let's try to refine these bounds so that we can understand where this should be. And we made a huge amount of progress on this problem under more assumptions. For example, when the entries are independent but are allowed to have different variances, and we have a series of papers about this, which I don't want to talk about today. But this very, very general model where you also allowed to have arbitrary dependencies was completely open. The methods we were developing for that were not what we followed. And in the last year, we certainly managed to make progress on this problem. But what was surprising is that, in fact, once we understood the right way to think about this problem, so one needs to have a different way of thinking about this problem than we were doing before. And once you have the right way of thinking about this problem, it turns out that you can actually do much, much more than this very modest goal, right? This modest goal was just to try to have some sort of inequalities that are slightly better than these. But in hindsight, it turns out that actually we can have almost the best of both worlds. We can take a random matrix like this, which is almost completely arbitrary, And under very mild assumptions, we cannot just get inequalities up to constants. We can predict with complete accuracy the precise behavior of the spectrum. We can have sharp constants even, right? We can predict this up to 1 plus little o1. We can actually predict the spectral distribution, the histogram of the eigenvalues. And we can, so in some sense, it turns out now, and in the rest of this talk, I'm going to try to explain what this theory looks like. But it turns out that actually it is possible, completely unexpectedly, to have a theory that takes such a completely general model and provides the same kind of information that you can get in classical random matrix theory in the asymptotic regime. And this to us was very surprising. And it is not possible in complete generality, but under extremely mild assumptions, which exactly cut off the examples like this where such things are not. And so in the rest of this talk, I want to explain to you what this theory looks like. I want to at least give some sort of, hand wave the overview of how this. Are there any questions so far? So until further notice, I'm going to work with this model, this Gaussian model. Okay, at the very end of the talk, I'll say something about non-Gaussian. So until further notice, x is d by d. Let's say self-adjoint and jointly Gaussian. And I'm now even allowing it to have non-zero mean. Maybe don't care zero mean assumption. So here is the high level area. So we start with such a random matrix X. So this is our given. So this, what is this object? Right? X is a d by d random matrix. Now, what we're going to do is to every such random matrix, we're going to associate a different object that's defined by the model of this random matrix. It's called X3. And the way that you should think about this object, so I'm not going to define it completely in this stuff. I'm not going to define it rigorously. But this X3 is not a random matrix. It's a certain deterministic object. Infinite dimensional operator. And the way it's defined, I'll just hand wave it. What you do, right? So this is a d by d matrix. In order to define this object X3, what you do is you start with the original d by d matrix. So its entries have a certain mean and covariance. And what you do is you replace each entry here, which is a random variable, by a certain non-commutative version of this random variable called the semicircular system. And what you do is you choose this semicircular system to have the same mean and covariance as the original. Okay. So if you've never heard of this, then this will mean nothing to you. But for the purposes of this talk, we don't need to understand how this thing is constructed. This is some sort of construction that exists in the literature, in the theory of operator algebras. Okay. So let's just take it for granted. But the point is that to every random matrix is associated a certain deterministic operator, which you should think about as a sort of Platonic ideal associated to this random matrix. This is a sort of ideal model, right? It's a sort of idealized model of this particular random matrix that we hope captures its spectral properties. Yes?
So, I mean, I'm extremely ignorant of these topics and maybe a few other people in the room as well. So speaking only for us,
yes.
I think I heard you say that these are the folks in operator algebra that came up with this object.
Yes.
They're not probabilists, and they're the ones who invented this object.
Yes.
Okay.
I can say more about this, but I will say very little about this in a moment. There's a so-called free probability theory of Voiculescu where this thing comes up, and it was developed not for the purposes of probability. It was developed for the purposes of making progress towards the classification of von Neumann algebras, which is a very old problem in this area. But the connection between free probability and random matrices is very well known and very well understood. It's something that was developed in the 90s. And I think a lot of the importance of free probability comes from its connection to random matrix theory. So we certainly did not invent the connection between free probability and random matrices. But I'll try to explain in a moment what the distinction is between what we're doing and what is known about free probability. So, but for the purposes of this talk, I don't want to define exactly how it is, but it has a very concrete definition and it's well understood what this object is, right? So for the purpose of this talk, we're just going to work. But just to give you some sort of idea, how you should think about this X3, right? In the simplest possible terms, right? If X is a Wigner matrix, the usual, the classical model of random matrix theory, right? Then I drew this picture before, right? I drew this picture of the semicircle, right? This is the histogram of the eigenvalues, right? But what this picture really means is that if I let D go to infinity, right, then the spectral distribution of the histogram of the eigenvalues will converge to this semicircle, right? But the point of this X3 is that this, right? So the spectral distribution of this object X3 associated to the Wigner matrix already equals the semicircle. This is an infinite dimensional operator, so it has a continuous limit, right? And this object actually has the semicircle distribution as its actual spectral distribution. There is no limit here, right? So you can think in this example, you can think of X3 as being like the D to infinity limit of this object. So it's the idealized form of this. Of course, here we are in an asymptotic regime, right? Whereas in our model, we don't have any asymptotic. But you know, you can think about this X3 as being an object that already has these kind of things as this spectrum with an equal, not with a limit. Now, the theory of free probability it gives a sort of calculus that enables exact computation of the spectrum of these objects. So even though these objects, if you're not used to them, are very complicated, and I haven't really told you how they're defined, etc., right? In practice, right, if you know how to deal with these kind of objects, the beauty of these objects X3 is that you can compute everything about them, right? For example, we have equations, even if it's not a semicircle in complicated situations, we can write down a system of equations that describes the exact distribution of this X3, right? So this is not a random matrix that we have to take limits. There's no asymptotics, right? These objects X3 are things that we can sit down and just compute, right? We have formulas for this. Good. Now, what is known about these objects X3? So the connection between random matrices and free probability is very much known. It's in fact very important. But what the theory of free probability gives in connection with random matrices is it is known how to construct a sequence of random matrices of increasing dimension whose spectral distributions will converge to the spectral distribution of X3. And let me explain how you do that. Suppose that I wanted to find, right? So this X3, the way I define it is it's some sort of matrix of operators, of non-commutative objects that has the same mean and covariance as X. Free probability theory will tell you, it will provide a recipe for constructing a sequence of random matrices, not a dimension D, but with dimension going to infinity, whose spectral distributions converge to that of X3. How do you do it? You start with the original D by D random matrix. And then every entry of the matrix, you replace it by an n by n Wigner matrix. So now you get a dn times dn dimensional matrix. Right? And each of these Wigner matrices, you make them for different entries of the original matrix X. You make those Wigner matrices have the same mean and covariance as the scalar entries of the original matrix X. Does that make sense? So what you can do is you can start with the original matrix, blow up each of the entries into a random matrix itself, and let the dimension of these entries go to infinity, right? And free probability theory will tell you that if you do that, if you blow up each entry into a whole random matrix and let the dimension go to infinity, then in the limit, the spectrum of those blown up matrices will converge to the spectrum of this object X3, which we can compute explicitly using formulas. Roughly speaking, the upshot of our theory is that in many cases, this convergence is already set in the original matrix with the scalar. And that's a completely unexpected phenomenon. You don't need to blow up the entries of this matrix into high and take asymptotic limits. Actually, for almost all random matrices X, and I will say in a moment what is almost all, the behavior of this original scalar random matrix X is already like this. Which means that we can actually understand the behavior not just of special models of random matrices using free probability. We can actually understand the behavior of almost any random matrix. And that's a completely new ingredient to the story that was missing in the theory of free probability. So of course, this cannot be true always, because for example, here in the example of the diagonal matrix, that's very, very, very false. Okay? So we have to understand what are the right things. So just to compare this with the non-communication inequality, let me write down one result that we so this is just one theorem, but actually the techniques that we have allows to prove many different things that later on I will write a whole bunch of things that we can show using these methods, right? So I'm writing something now. I'm going to give you an inequality for the norm of X, just so you can compare that with the non-communication inequality, right? So we can say things not just about the norm of X, but just so we can compare with the best result that was done before. Let's give it an inequality. So this is with Alfonso Bandera, so I have to introduce a certain quantity that will capture when this approximation. So let me call it, so I call it cov of X, the covariance matrix of X. Right? So remember, X is a D by D matrix. So it has D squared entries, right? So we call cov of X, this is the D squared by D squared covariance matrix of the entries. So a D by D random matrix X has D squared entries, so we could just write down a D squared by D squared covariance matrix. And one inequality of non-communication type is the following. So the largest eigenvalue of X is bounded by the largest eigenvalue of X3, and I notice that there's a constant 1 here, right? It's not just an estimate. This is with a constant 1. Plus some universal constant. And here we get the parameters that we'll discuss in a moment. And we still get some sort of log D term. So here in our bounds, we get log D. So there is a log D term here. In non-communication, the log D term, maybe I should make a remark to help you interpret this. So free probability theory gives us the following is. So this quantity that was in non-communication is just up to a factor 2, just an upper bound of the largest eigenvalue of this X. So if you plug this into this estimate, right, the non-commutative kinship inequality gives you that the expected norm of X is bounded by this quantity times square root log D. But here we don't get this times square root log D. We get a constant 1. Right? Of course, we still must have somewhere a log D, because, for example, the example of the diagonal matrix, we have to have a log D. But the log D here is in the second term. So for the diagonal matrix, these objects over here are of the same order as that, and we don't win. But for example, for Wigner matrix, these objects over here are very, very small. They're of order 1 over D to 1/4 or something like that, right? And therefore, this second term becomes negligible, and we have actually lost the square root log in non-communication. So in particular, this shows the square root log d in non-commutative function can be removed if the norm of the covariance matrix of x divided by the norm of the expectation of x squared is much, much less than 1 over log d. And notice that both of these quantities are explicitly computable because they only depend on the covariance matrix. So now you see also the difference between those two examples I picked. In the diagonal matrix example, right, the covariance matrix of the entries, right, most of the entries were 0. So the covariance matrix of the entries, its norm is just 1. And this is also 1, right? Because you have Gaussian variables of mean 0 variance 1. So this is of order 1, which is not much less than 1. So this condition doesn't hold for the diagonal matrix. But for the Wigner matrix, the entries have variance 1 over d, right? So for Wigner matrices, this ratio here is 1 over d, which is much, much, much smaller than 1 over log d. So not only do Wigner matrices have better bounds, they're very, very far away from the border where you see this type of behavior. In fact, the log d would be enough, right? Wigner matrices get 1 over d. So for example, this theorem shows that even if you have extremely, extremely sparse matrices, matrices which only have, let's say, log d or so entries, non-zero entries in every row, that's already enough to remove the square root log d factor, which is very far away from the regime where classical random matrices is used. Good? Yes.
Do you know anything about the universal constant K there? Is that it just exists some constant, or do you know less than 100?
I mean, we can compute this from the proof. It's explicit, but we didn't bother. And you know, this is just one result. So we have. I mean, yeah. There is no point in computing that constant because we don't usually need. You see, we have here 3/4 on log d. It should be 1/2, really, right? And these are Gaussian matrices. That's an artifact of the proof. But I'm very unmotivated to do that because you see, this theorem is exactly of interest when this term becomes negligible, right? So, I mean, yes, there is some interest in improving that, but you know, whether you have 1 over log d cubed or 1 over log d here, in practice, really makes very little difference. But yes, I mean, this theorem, the second order term, is not fully believed to be optimal. I have some very detailed things to say about whether one cannot expect a much better type of theorem, but this I think goes beyond what I can say. You can ask me. Yes.
Professor Peterson's question that would actually be relevant in situations kind of like mesoscopic where D isn't super large, and then we really need to have a handle on how K compares to 1D.
Yeah. Okay. Of course, you know, you can expect. So we have many different variants of these kinds of bounds. Some of them have very small constants, like 2. This particular one has a larger constant, but I didn't bother. So, but if you really wanted to, you could do this. And some of it, like we have results, for example, not for the norm, but for the moments. And this is much easier than the norm bounds. And there the constants are much smaller. You know, they're like 2, 1 over square root. We get something there. So, yeah. What time is it? I can't tell what the minute of the hour. It's 10. So I have like 20 minutes, right? So is that right? Okay. All right. Yes. Arithmetic is not my strong. So I want to, before I tell you what the theory says more generally, I want to just give you a couple of examples to, I mean, I'm not going to work them out in detail, but I just want to give you a couple of examples to see that this kind of results are very easy to use and give you very strong results. So one example is that, you know, these kind of bounds give you, in specific situations, they give you bounds that are very easy to compute and that you can use instead of the non-commutative function inequality to get much better results in many situations. Right? So just to give some addition, I'm now going to do some additional structure to these matrices, but still rather general, and just to show you that you get sort of very concrete one. So suppose we take a matrix of independent columns. Right? So we have x1, x2, etc. Now for this example, let me make this a d by n matrix. Just for the heck of it. Or we could do d by d, whatever. It doesn't really matter. So this is no longer a symmetric matrix. Not self-adjusting. That's not a problem, because when you look at the norm of the matrix, the norm of the matrix X is always the same as the norm of this matrix. This is a standard trick in matrix theory. The norm of a non-symmetric matrix is the same as the norm of this symmetric matrix. So if we want to deal with non-symmetric matrices, we just plug this matrix into there. Because we can deal with arbitrary structure, that's no price for us. Right? So, the results here are going to transfer. So let's say, right, so these columns, x1 to x3, are independent. And the ith column is Gaussian between 0, but let's say some arbitrary covariance matrix CI. Right? So I've introduced extra structure, I've made the columns independent. But I'm allowing dependencies inside the columns, arbitrary dependencies, and arbitrary variances. I didn't do this because we cannot handle something more general, but just because to get a clean bound to show you how easy it is to use this result. If you plug that in here and use some estimate like this, you get some very explicit bounds. You get the bound looks like this. The expected norm of x is bounded by, so you get the norm sum I plus the maximum traces. Plus, now we get this constant, maximum I of the norm of Ci, and well, some bounds. So this just comes out if you plug in some estimates over here. And the point here is not to digest this precisely what it means, but simply to show that these are very explicit inequalities, that if I give you any sort of random matrix, you can compute all of these quantities over here, right? And in particular, right, so in non-commutative kinship would give you such an inequality, it would give you this term times square root log d. But here, not only do you not have times square root log d, you have a constant 1, which is the best possible constant. On the other hand, you see here that the remainder term, right? The remainder term, this norm of the covariance matrix will be the maximum of the largest eigenvalues of the covariance matrices. But the leading term is already the maximum of the traces of the covariance matrix. So of course, if you had the example of a diagonal matrix, right? When you had just diagonal Gaussian entries, each of these covariance matrices are rank 1. So then the trace and the norm are the same. And then this term over here will be too large, right? But that's exactly the example where this theory doesn't work, where non-commutative kinship is sharp. But as soon as these as soon as the trace of the covariance matrices of the columns are just a little bit larger by a factor logarithm that I mentioned, than their largest eigenvalues, right? Because this is the sum of the eigenvalues, this is the maximum of the eigenvalues. As soon as the sum of the eigenvalues of the covariance matrices just a little bit exceeds the largest eigenvalue, which is a very mild assumption, we're already in the regime of classical random matrices, right? And we can use this free model to predict what's going on up to with a universal. So, these type of inequalities give you tools that you can hit on your problems. They're very easy to use. Now, I want to give you another example. Just to illustrate what kind of phenomena you can study with this that would be completely out of the question with non-commutative kinship inequality or classical inequalities of this kind. So this is actually a classical example in random matrix theory. Suppose I take a Wigner matrix. The matrix of I of D Gaussian matrix, variance 1 over D, right? So this just behaves like a semicircle, classical model. Suppose I add a rank 1 matrix to it. So V is some deterministic vector, unit vector, and theta is just a constant. But this model, this is called a spiked covariance matrix. It was studied in a famous paper by Bike and Nabus and Fisher. And what they showed is, right, so if you have this Wigner matrix, right, the second guy over here, its spectrum looks as d goes to infinity like this semicircle, right? But now it added a deterministic rank 1 vector, right? So you can imagine if that parameter theta is small, I add a very small deterministic rank 1 vector, then that extra eigenvalue will end up somewhere over here inside the spectrum where you won't see it, right? But if you take theta to be very large, then there should be an eigenvalue that pops out, right? That's caused by this rank 1 perturbation. Right? And what they proved is that that happens exactly when theta is more than 1, so you get this outlier. At 1 over theta plus theta, if theta is greater than 1. If theta is less or equal 1, this extra eigenvalue is lost in the bulk. And if theta is greater than 1, there's a phase transition and an outlier eigenvalue pops out of the bulk and sits over here at location 1 over theta plus theta. This was proved using methods of classical random matrix theory, right? And explicit computation. But in principle, you see, I mean, this is just a matrix with jointly Gaussian entries, arbitrary mean, arbitrary covariance, right? So we should be able to compute such things from our type of theory. And in fact, it's very easy because we have an explicit formula, some free probability theory, at the max of x free. There's an explicit formula. It looks like this. It's the infimum over positive depth of matrices of the largest eigenvalue of m inverse plus the expectation of x plus the expectation of x bar and x bar, where x bar is the center of the matrix. So, okay, it's some sort of variational principle. But it's an exact formula coming from free probability that you can just use. Right? And what it means is that if you know, which is very trivial here from our bounds, because in our bounds, this term over here will be like polynomially small indeed, but it will be negligible compared to this term, right? And it means that once you understand that, studying these kind of phenomena just reduces to understanding this deterministic problem. Now, in some cases that may be hard, and in some cases that may be easy, but it's a deterministic problem. There's no random matrix problem left. And in this particular example, it turns out to be very easy to solve this optimization. It's very easy to show that the limit as d goes to infinity of larger eigenvalue of x free is 2. Theta plus or equal to 1, and it's 1 over theta plus theta. I won't do the computation, but you just, you plug these matrices in here and then you see that everything collapses. So you see, the point of this theory is, okay, in other situations, for example, now you could ask other questions, like let's say that I replace this Wigner matrix now by a structured one, by a sparse matrix, for example. Do we have similar phenomena, right? In principle, right, it could be that solving this deterministic problem now becomes harder, right? But what the theory shows is that the whole problem is reduced to a deterministic problem, right? And that is what it is. You will have to solve that deterministic. But the random matrix theory is taken out of view. Yes?
Even if it's hard, it's a deterministic problem. It could be approximate.
It could be approximated, yeah. Right? Actually, if you're interested in computational complexity, it is not clear to me whether this is an NP-hard problem or not. This is not my area of expertise. I've asked experts in theoretical computer science, and they told me they don't know. So, but it could be approximated, yes. Yes, you can find estimates, right? But I would say also that it is what it is, right? I mean, the point is that if you have such a random matrix, it is often very easy to show that this term is negligible. And what our theory then shows is that this is the actual answer, right? So if the deterministic problem is hard, well, this problem is hard, right? I mean, you see the same thing in statistical physics, right? In statistical physics, there are certain mean field models, right? And the mean field theory is often described by some sort of variation principle that's coming from large deviations, right? Now, large deviations theory will tell you that the random problem behaves as some asymptotic regime, like the deterministic problem, like some deterministic variational principle. Solving that variational principle can itself be a difficult problem, right? But it is what it is. That's the problem, right? And here is an analogous situation in random matrix theory, right? Where what the theory shows is that this random problem behaves exactly like a deterministic problem. The deterministic problem is what it is. You have to solve it if you want to understand. Very good. So let me give you a summary of so up to now, I've just written down one inequality. And it's even just an upper bound. I talk as though this is exact because I have a constant one. It's just an upper bound. But actually, we also have lower bounds that show that x3 is also lower. And we have much more than the norm. So let me just give you some sort of summary of the kind of things we do. So the whole thing revolves around this kind of condition. As soon as this condition is satisfied over here, the random matrix X behaves like a 3 number. So let me write it down. So there is some condition that looks like this. As soon as this condition, which is explicitly computable, because everything here is an explicit function of the covariance matrix. So what happens? So first of all, the spectral distribution, not just the norm, but the spectral distribution of X will be close to the spectral distribution of X. So not just do we know something about the extreme eigenvalues, you can draw the histogram of the eigenvalues. The whole histogram of X, of the eigenvalues of X, will be close to the deterministic histogram of the deterministic operator, of the spectrum of that operator. Now, in general, this operator X3 will not have the semicircle. Typically, it looks sort of complicated. It has some, it looks like a bunch of blobs. Here is a typical type of, right? It's the histogram of X3. The spectral distribution of X3 typically looks something like that. You have a bunch of blobs with these strange shapes. Okay? But whatever it is, we can compute explicitly because we have explicit systems of equations that describe this. Okay? So that is what it is, right? And our theory says that if you have this assumption, then the histogram of the eigenvalues of X will look like this. Then you just have to compute this, which is the deterministic. Secondly, as I said before, the histogram itself says nothing about the extreme eigenvalues, right? Because if you have a single outlier eigenvalue, it has mass 1 over b in the histogram, right? So it doesn't see it. But what the theory says is that not just do the extreme eigenvalues converge to the extreme eigenvalues over here in this histogram, but in fact, you cannot have any eigenvalues also in the X. Right? So you can have no eigenvalues here, no eigenvalues here, right? So asymptotic or asymptotic, under this assumption, all of the eigenvalues of X have to be very close to the support of the spectral distribution. So statements such as that inequality over there, right, are immediate consequence of this problem. Really what we say is that all eigenvalues have to be within distance of the second order term of the spectrum of X3, and then, you know, this type of statement follows, but also you cannot have any eigenvalues here or here. Then, same for polynomials of such units. If I take a bunch of random matrices x1, x2, x3, x4, etc., out of jointly Gaussian entries, I can take some polynomials of them. X1 times x2 times x1 minus x3 cubed times x1 to the fifth, you know, make itself a joint to the below value. Take some weird polynomial, right? And our theory says that the spectrum of this weird polynomial, right? Whatever it is, it will, under this condition, it will be very close to the spectrum of that same polynomial, but of the x3s. And then you can use free probability to try to compute the spectrum of that polynomial, which is a pain in the ass in most examples, but right? It's a deterministic problem. Right? So in particular, for example, if you think about sample covariance matrices, x transpose, that's just a quadratic polynomial. Right? So sample covariance matrices are a very special case of this, right? And they behave like that for example. Right? So in statistics, for example, it's very important. And for all of this is non-asymptotic. Well, it's non-asymptotic by default, right? But because the questions are non-asymptotic. But what I mean is we have explicit inequalities that describe all of these behaviors. As you know, explicit inequalities depending only on parameters. So they can be used as ingredients in other analysis. Right? And maybe I should make a point that when I write something like this with much, much less than, right? It looks a little bit like I'm talking about asymptotics, right? Because usually when I write something like this, I mean that as d goes to infinity, right, log d cubed times this divided by that goes to 0, right? So it looks like I've hidden some asymptotics, right? But you should be very careful with the interpretation, right? Because what our theory says is that for every given x, there is a model x3 that describes it well under this condition. But this model depends on the dimension d of the original model, right? This is a d by d matrix of random variables, and this is a d by d matrix of deterministic operators, right? So indeed, if I let d go, if I have a sequence of such models as d goes to infinity, and this condition is satisfied, and as d goes to infinity, the behavior of x3 becomes exact, right? But the point here is that x3 is also changing. It's not just x that's changing, it's also x3 that's changing. So there doesn't have to be a limiting free model. It says that for every fixed dimension d, the model in that dimension is close to its equivalent. And this is very important, for example, in applications like this. So in applications like this, you see what happens here is in the limit, you have a single outlier eigenvalue. But the single outlier eigenvalue will not be seen in the spectrum of x3 because it has mass 0. But for finite d, the spectrum of x3 will not look like this with a single eigenvalue. Right? In the limit, it will look like a single eigenvalue. But for finite d, the spectrum of x3 will have like a little blob over here, centered at 1 over theta plus theta, but it will have mass 1 over d. And this blob will have mass 1 minus 1 over d. And so in the limit, as d goes to infinity, you still see that outlier, right? But its mass goes to 0. So there is no limiting x3. If you took the limit of the x3s, you would no longer see this eigenvalue. So you have here a sequence of x3s, and in order to see that eigenvalue, you need to be able to have this non-asymptotic point of view. Right? So it's really a non-asymptotic. Very good. In my last minute, I just want to say a word about non-Gaussian. So everything I've said so far about Gaussian matrices, which join the Gaussian matrices, this is extremely general. But you know, in practice, often when it comes to non-Gaussian matrices, now you know, just to say that I have any random matrix, any entries, any distribution, this is too much. You know, we cannot hope to say something like that. But in the applied math literature, there is a certain type of model of random matrices that proved to be extremely useful. Which is what happens if you take a random matrix to be a sum of independent random matrices. For example, if you have a jointly Gaussian matrix, you can always think of it as being such a sum. Right? Jointly Gaussian. You can always view it as being a deterministic matrix plus a linear combination of scalar Gaussian and some deterministic matrix. Right? But if I have a matrix, for example, with independent entries with arbitrary distribution, right? You could also write it like this. You could write a sum ij of some independent random variables, right, times the matrix which has a 1 in the ij component and 0. Right? So you see many non-Gaussian random matrices also follow this. And basically what we have understood is that this whole theory of Gaussian, this whole Gaussian theory, non-asymptotic theory, extends beautifully to this kind of thing. But actually, it turns out this has nothing to do with the original theory. It turns out there is a separate principle. There is some other parameter, not the normal covariance matrix, some other parameter, such that if this ratio is smaller than something like power log d, then in all of these ways, the spectrum of x behaves like the spectrum of the Gaussian random matrix, whose entries have the same covariance. And this is a kind of central limit theorem, if you will. Right? But it's a central limit theorem that kicks in not when you have a polynomial size, you know, the polynomial area in D, but only log D. So it's for random matrices, the central limit theorem kicks in very quickly. And once you combine these two principles, you get a theory that is really very easily applicable. So let me end there. Thank you very much.
Do you have any questions?
They were already asked during the talk.
Question about the number 3 item. There is a simple polynomial of such matrix. What is the last word? Do you mean here the polynomial of the x and x3?
No. I mean, for example, right, if you wanted to look at a sample covariance matrix. So let's say I took X to have independent columns, then this would be the so-called sample covariance matrix. This is a polynomial of X of degree 2, right? So our theory will say that this behaves like X3 minus T, however you want to describe it.
Minus expectation x3.
Yeah, exactly. I mean, whatever expectation means for the statistic output.
Okay.
The trace, there's a trace, right?
The item number 4, you see all of this is not asymptotic. The x3 to asymptotic of x as equal to infinity. Right?
No. This is the whole point. X, for every matrix X, we have an X3. There is no asymptotics here, right? So there's a recipe starting from any random matrix X to construct X3 associated to that X.
Oh, I see.
And point 4 says that, for example, right, one gets such an info. Plus something that's small in this condition.
Here, are you considering the equation equal to infinity, or you just consider a very large d?
Even. I'm just considering a fixed D,
Okay.
but when this parameter is much smaller than 1 over log D cubed, this theory sets in because the leading term in these inequalities becomes dominant. Right? And there is no asymptotics. It doesn't make sense to have asymptotics because we're talking about a fixed D by D matrix X with an arbitrary structure. It's not, we don't have a sequence of X's in increasing D, right? So we cannot do asymptotics because there is no asymptotics.
Thank you.
Yes. Yes.
So if I assume that I do have a sequence of matrices that grow bigger and bigger, so are there normal conditions under which the x3 would, converge to a limit?
Yes. Yeah. So I mean, so I like this example because it exactly shows that even in this situation, even if you're interested in the asymptotics, you will not see the behavior you're interested in the asymptotics of X3. Right. So for example, in this model, the X3s, right, the X3 associated to this model as D goes to infinity just converges to the semicircle.
Right.
And this guy disappears. But in order to see the behavior you're looking for, you cannot look at the limiting X3. You have to look at it non-asymptotic.
So it's important not to switch the order.
Exactly. The order of limits doesn't commute, right? But there are, of course, many models for which there isn't. Actually, most models of classical random matrix theory have an associated limiting X3. And that's basically the classical theory of probability. So this is something very common, and for polynomials, this is something that's very important in probability theory. It turns out to go the other way. Frederick asked me earlier about operator algebras. Such theorems about polynomials of random matrices were used in order to prove theorems about operator algebras by Hagel and Turbionsi, who first considered such questions. So these kind of limiting objects are very important.
Can I follow up? If I may, we can leave the questions for the break.
Okay, we run out of time.
It's not again at 10:50. Session.
Thank you very much.